Well, okay, it is 3:30, so I guess we can go ahead and get started. Yeah, how's everyone doing? Hopefully good. So yeah, basically welcome to Stat 437, unsupervised learning. My name is Tori Ellison. You can call me Tori or you can call me Dr. Ellison. I will be your instructor here for this course. I wanted to give a quick caveat here. Right off the bat, I literally just finished teaching my previous Stat 207 class like 5 minutes ago. So if you're noticing that I'm a little bit out of breath, it is because I am. So I do aim to keep the same level of, enthusiasm and uh, breath, I guess you could say, for both of my classes. But the scheduling is a little bit tight, unfortunately, this semester. So we'll try to keep up the engagement here. But if you notice I'm a little bit out of breath some days, it's because I am. So yeah, I'm really excited for this course. I do think this is actually my favorite course to teach, for a variety of different reasons. So I'm yeah excited to be here. Excited that you guys are here. You decided to enroll in this class. So I'm sure that you've seen this is basically a online class. So we've all done the online Zoom class before, so I think we kind of have a sense as to best practices. So do make sure, unless you're actually, asking a question, do make sure you keep your mic off once you log into the class. Let me just get this little thing out of the way here. So yeah, I sent out an email a couple days ago, basically talking about a getting to know you survey. So unfortunately, for most of the class, I won't be able to, see you guys in person. So that getting to know you survey, I think, hoping that will help, bridge the gap, give you guys the opportunity to let me know things about you that can essentially best assist you as we're going through this online course here. Now, generally speaking, I don't really like teaching online classes. It's not my preference. Unfortunately, due to extenuating family circumstances, I do need to teach this course online for the most part, although I will be coming to campus a couple times throughout the semester. So we'll talk about this more as we get into the syllabus, but one of the key components of this course will be completing and presenting your final project. So generally speaking, the default, even though this is technically an online course for the most part, the default setting will be for you guys to actually present your research finding in person. However, if you know ahead of time that you are unable to, essentially be here in person on that date, do let me know as soon as possible and we can discuss backup options essentially. So yeah, so basically the default setting is to have some in-person part at the very end in which I will actually come and see you guys, hopefully give you positive feedback for your final reports. But again, if you have extenuating circumstances for why you can't be there in person on that final day, definitely let me know. We can discuss options. So yeah, I talked about in the online, or excuse me, the Getting to Know You survey, talked about a variety of different ways in which you can hopefully remain engaged in these online lectures. So like I mentioned, oh, actually, I guess I didn't mention this. So attendance for this class is not necessarily mandatory, but I would highly encourage it as it allows for you to remain engaged in the course. So if you'd like to, I definitely encourage you guys to, ask questions in the chat, answer questions in the chat. If you'd like to have even more of an interactive feel for this course, if you'd like to ask me a question or answer a question, you can always raise your hand, like with the Zoom option, essentially, and I can, call upon you, and we can have more of that in-person feel. And generally speaking, there's every semester there's, I think, about, you know, 10 to 20% of the students who really want that. So, if you're one of those people that actually does want to have that in-person feel, I'd say go for it. Definitely, this lecture structure is for you guys. So whatever you guys think that you need in order to help you, understand unsupervised learning to the fullest, definitely let me know, definitely engaged. So we're also going to be having a variety of, Zoom polls as well as breakout sessions to hopefully, keep that engagement as well. And yeah, basically, if there's anything else that you think that you might find helpful when it comes to staying engaged in these, online settings, definitely let me know, in that getting to know you survey. Okay, so a little bit about me. We'll get to so basically, I'm a teaching professor here in the statistics department. I've been here for 4 years. I also worked in the data science industry for about 6 years while I was getting my PhD in operations research. Now, this is always the part of the lecture that kind of depresses me a little bit, but just out of curiosity, has anybody actually heard of operations research? Does anybody actually know what it is? I usually get maybe one person per class who's actually heard of it. Anyone? Yes. Oh, cool. Somebody has heard of it. Yeah, it's so what it is it's basically an advanced form of mathematical optimization. So if you think back to your, you know, basic calculus classes where they're giving you those, mathematical optimization problems where they're like, you know, how do we maximize the volume of the pool given that the area of the base of the pool has to be a certain number? It's kind of like, it's using the same types of calculus-based techniques to answer questions such as that. But the cool thing about mathematical optimization or operations research is that we are learning tools. We're given the tools that allow for us to answer much more exciting questions than optimizing pool volumes, if you will. So I worked for 3 companies while I was, working in the industry. I worked in, online advertising, TV advertising, as well as narcotics detection. So for instance, we were asking questions about how do we, for instance, what are the optimal commercial spots to place a given advertiser's commercial such that we're maximizing the total reach of the target audience that we wanted to, essentially have exposed to our particular product. So interesting stuff like that. Also, I'll ask this question here first as well. So this class, unsupervised learning, what is it? What are we doing here? Does anyone know what is unsupervised learning? We just kind of signed up for this class. We rolled the dice, hope for the best. Computer does the research for us. Yeah, I mean, so we are going to be using mathematical algorithms. Yeah, analyzing data without a set output. Yeah, exactly. Training models where we don't have a response variable. I always ask this question because it's I'm not sure if you guys know this, but this course actually it started out as a Stat 430 special topics class. And it actually took a very long time to turn this class into its own distinct number. Part of which is because we had to have a couple deans approve the process. And so when we were submitting, or when I was submitting the application to turn this into a real class, a lot of the deans were thinking that unsupervised learning meant that essentially this sort of just some sort of groovy free-for-all, you guys are basically just learning whatever you want and I'm not really supervising you. So the unsupervised part actually corresponds to the fact that we don't actually have a fixed response variable in our hands. So we'll talk a little bit more about what unsupervised learning is as we move on into the class. But basically, one of the reasons why I love unsupervised learning is because I did basically all of my dissertation in cluster analysis, which is one of the key types of unsupervised learning analyses. So for instance, I used mathematical optimization to design a new type of clustering algorithm that works better for a particular type of data set. So something that we're going to be learning in this class is that there's tons of different clustering algorithms. There's basically tons of different unsupervised learning algorithms that exist out there. So one of the things we're going to be doing in this class is basically giving you a roadmap as to the wide variety of different algorithms that exist and why you might want to use those particular algorithms. And basically, I'll kind of give you a spoiler here. It's all based on your data. So some unsupervised learning algorithms are going to be really effective, for instance, at clustering some data sets, whereas other clustering algorithms are going to be better at clustering other types of data sets. So it's all about the data that you're dealing with. So yeah, in particular, I was using these data sets in my dissertation to cluster gene expression profiles. So one of the interesting things about clustering gene profiles, for instance, is that medical research allows for medical researchers to identify very unique idiosyncratic subtypes of diseases. So for instance, if you cluster a data set of breast tumors based on their genes, you might actually find different types of breast cancers in which you can develop more effective micro-targeted therapies for. So it's really cool stuff. So yeah, so enough about me. I want to learn a little bit more about you guys. One of the ways that I want to do that is through the Getting to Know You survey. But also I'd like to learn a little bit more about, what kind of data sets do you find interesting, or what types of research applications are you interested in that perhaps you'd like to apply these unsupervised learning techniques to. Also, I'd like to give you guys an opportunity to, meet some other people in the class. So what I'm going to do in just a second is I'm going to open up the breakout rooms. You can choose your own breakout room. I'd suggest going to a group with about 4 people. And yeah, basically, when you're in your breakout room, if you could go around and basically say your name, say what your major is in or what you're studying, like what year you are. And then also basically, talk about what types of research applications or data sets that you find interesting. So we'll open up the breakout rooms. We'll meet back in 5 minutes to discuss. And really curious to see what you guys are interested in. Okay. I've just opened up the breakout rooms. In the interest of time, I'll just start randomly assigning people to groups, but you can always change the group if you'd like to. Okay, so everybody should be assigned to a group now. So we will meet back in a few minutes and discuss. Okay, we'll give it a few seconds for people to come back to the main room. But yeah, curious to hear what you guys were talking about. So yeah, what types of data sets or research applications would you like to apply unsupervised learning techniques to? What kind of data sets are you passionate about? What are you interested in? Put it in the chat. Cool. Movie data sets. Yeah, movie data sets are going to be really interesting. One of the algorithms that we're going to talk about more towards the end of class, non-negative matrix factorization, is basically more or less designed for the Netflix data set in mind. So basically, the rows are the users and the columns are the movies that people have watched. Yeah, so sports, public transportation, biomedical, biostats, tourism. Cool, tourism. That's actually some the data set that we're going to be working on in our first unit. Good deal. Pharmaceutical recommendations. Yeah, so a lot of these data sets are really well designed for unsupervised learning techniques. So what we're going to be discovering in this class is basically how do we take high dimensional data sets like the ones that you mentioned, and how do we unlock hidden insights from those data sets that we're not able to see with our eyes, if we were like simply just looking at a two-dimensional data set. So yeah, I definitely like to learn more about you guys in any ways that I can further help you basically reach your career goals in this class. So feel free to drop by in office hours. Feel free to ask me any questions that you might have after class. But yeah, just generally, looking forward to getting to know you guys. In addition to the syllabus, you have a final group project. Now, I do realize because this is an online class, perhaps you may have less opportunities to get to know people. So therefore, I would suggest, coming to these lectures so we can have, those so you can go to the breakout rooms, for instance, and get to know some of your classmates might be a way of, sussing out if somebody might be a good project partner or not. So something to think about. So yeah, wanted to move on before getting into the nitty-gritty details of the class. I'd like to learn, discuss a little bit more about, what is unsupervised learning? What is machine learning? And where does it fit into what we call the full data science pipeline? So first we'll talk about, what is the data science pipeline? So basically, given that I was a industry data scientist for 6 years, I never liked to teach my classes in like this petri dish kind of fashion. I very much like to get us thinking about how do we incorporate these algorithms that we're going to be learning in the class into the scope of completing a full beginning to end data science analysis. So generally speaking, when we talk about the data science pipeline, this represents the set of sub questions or sub analyses that we would want to think about when it comes to essentially pursuing some sort of a goal or solving some sort of a problem with data. So for instance, that usually starts with formulating some sort of question or research goal that you can accomplish with the data set. It involves thinking about, how do we collect data that most effectively helps us answer that question or, pursue that goal. It gets us thinking about, once we've collected our data, how do we store the data? How do we extract it most effectively? It has us thinking about, how do we clean the data? How do we represent it in a different way such that we're most able to, answer that question or pursue that goal? And then it also has us thinking about, well, how do we visualize? How do we describe our data set? Now, something that we're going to discuss is that basically unsupervised learning is more or less just a more sophisticated way of describing the data set. So that's ultimately what our goal is. So, if we have a smaller data set, more basic descriptive analytics techniques are simply just creating, visualizations, making a histogram, making a scatter plot. But the problem is, when we're dealing with these high dimensional data sets, we can't necessarily see all of the hidden insights with our eyes. So unsupervised learning algorithms come in handy because it allows for us to extract those insights about data sets that we can't actually visualize completely, because we can only see in 3 dimensions. Another part or aspect, perhaps, of the data science pipeline is perhaps using your data set to, make predictions with a given data set that you have. So now this is actually going to map on, or essentially this is the main goal of the other type of machine learning analysis, which we call supervised learning. So in that case, that's different from unsupervised learning in that we were actually given a response variable in our hands. And our overall goal is to, take our explanatory variables that we have in our hands and most effectively predict that response variable. Some other techniques or some other things that we do in data science, we might conduct inference. And then finally, and this is actually, this is my favorite part of the data science pipeline, so prescriptive analytics. So essentially, what is the prescription, or how do we make the best decisions, for our industry or our organization based on the insights that we've collected here. So this is actually essentially, this is what operations research is. How do we make the best decisions? So basically, when we're conducting an unsupervised learning analysis, we never want to just basically apply k-means to our data set and call it a day. As we're going through this class, we want to be deeply thinking about how might other decisions or insights that we've found throughout other parts of the pipeline, how might that affect, for instance, what unsupervised learning algorithm that we use, or perhaps how we interpret our insights. And furthermore, once we use our unsupervised learning algorithm, how might we use those insights, for instance, to make good decisions? So we're really going to be mimicking the general process, I guess you could say, of what a full, a real data scientist might engage in as they're applying an unsupervised learning analysis. So any questions on that? Okay, cool. And so basically, just a little bit more about machine learning, supervised learning. So basically, machine learning, it's essentially just a branch of computer science where we are using data essentially to implement either descriptive models or predictive models. And again, just to summarize what I just said there, unsupervised learning are basically, more sophisticated types of descriptive analytics algorithms, and supervised learning algorithms are basically types of predictive analytics algorithms. Okay. And so something I wanted to mention is, you can find these notes that we'll be filling out in the class. So I'll always post a zip file with basically a skeleton PDF that we will fill out in the, during the lecture. So basically by the morning of the lecture, you should be able to find these notes. So I would suggest, downloading these notes ahead of time. If you're a person who likes print copies, you can, I'd suggest printing them out ahead of time. So usually in each of these zip files, you'll find a PDF with skeleton notes that we'll fill out in class, as well as a Jupyter notebook and a CSV file that we'll also go over in class. So basically that'll be the application of the techniques that we'll talk about in the PDF. So something to keep in mind. Also, I just wanted to mention this as well. So I would definitely say, I would definitely suggest taking your own notes. But if you find that I'm going a little bit too fast or there's something that you wanted to review, I do post all of my videos as well as notes on Canvas. So if you go to our Canvas page, so if you go to our Canvas page here, within 24 hours, you should be able to see a recording of the lecture here under the post-lecture videos tab. Canvas is running very slowly. And then furthermore, if you go to the files tab, you should be able to see a copy of everything that I'm writing here. So basically a markup of the PDF. So do keep that in mind, but I would suggest, taking your own diligent notes as well. Okay, so two types of machine learning, unsupervised learning and supervised learning algorithms. Now I want to talk a little bit more about the key assumptions that basically all machine learning algorithms essentially assume, regardless of whether it's a supervised or unsupervised learning algorithm. So for all machine learning analyses, there's always three elements involved, essentially. So number one, we always have some sort of set of feature vectors or a set of explanatory variable values in a data set. So for instance, one example might be a, features matrix or a set of, high school graduation rates, college graduation rates, and insurance rates for a set of US counties, for instance. In addition, whether implicitly or explicitly, there's always a set of what we call target values, or perhaps labels or response variable values. And so, for instance, this might be the poverty rate of a set of US counties. Now, generally speaking, regardless of whether it's a unsupervised or a supervised learning algorithm, our goal is to basically come up, or basically there's always this assumption that there is some sort of fixed or unknown mapping function that maps our explanatory variable values to our response variable values. So we usually have a random error term that's assumed as well that is involved in this mapping function. And so there's, a variety of assumptions perhaps that, we might make about perhaps what this mapping function is. And then basically that assumption that we make is going to dictate the suite or the types of mapping functions that we might be considering. So for instance, if we think about like a basic linear regression, that would be an example of a supervised learning algorithm, because we're actually given, or we can assume that we've actually been given our set of response variable values, or the poverty rates. And so what we do when fitting a linear regression model is that we make the assumption that basically this fixed unknown mapping function is in fact linear. And so our goal of this particular type of supervised learning analysis is to basically search through all possible linear mapping functions, which is basically comprised of a intercept as well as slopes, that best predict our given response variable value y. Okay, so the key thing here is in a supervised learning algorithm, it is assumed that your response variable value in your data set is known. You have it in your hands. And so for a general supervised learning analysis, our theoretical goal, again, is to basically, out of all possible mapping functions, choose the best function, we call g hat, such that g hat of x is as close as possible to our given set of response variable values. Now, there's actually a couple of vague things that I've basically said when stating this theoretical goal. So there's actually two, I would say. So what are some vague elements of this goal here? Yeah, so one vague concept is, we might ask the question, what do we mean by best? Yep, so that's one follow-up question that we might have. And then anything else? Yeah, exactly. So we're saying as close as possible, but yeah, that begs the question, what do we mean by close? I mean, so for instance, one measure of closeness that we use is like, in a linear regression model is, is the sum square of the residuals, is that as small as possible? But the sum square of the residuals is not the only function that we might use to measure the closeness, for instance, of our predicted response variable values or our actual response variable values. So for instance, some people use the sum of the absolute value of the residuals. And that would be, for instance, another way to measure closeness. So we keep, in the beginning, when we're first introducing these concepts, we keep our goals, or our theoretical goals, vague or as broad as possible, because basically the way in which we would go about defining these vague elements of the statement actually dictate all of the many different machine learning algorithms that might exist. So in some data sets, using the sum square of the residuals to measure closeness would be a good idea. Whereas in other data sets, using the sum of the absolute value of the residuals might be a better idea. And now another caveat that we want to keep in mind here is that this is purely just our theoretical goal. In practicality, though, it's entirely possible that we may not actually care about learning what this g hat function actually is. So for the purpose of a supervised learning analysis, sometimes we care simply about, do we just get the best predictions? We don't necessarily care about interpreting, our function, our fitted function. Now, the nice thing about a linear regression model is that it's actually quite easy to interpret a linear regression model. It's basically just looking at a bunch of coefficients and the intercept, not too complicated. But can we think of any other supervised learning analyses in which the function or the mapping process that maps our explanatory variables to our response variables, can we think of any other supervised learning techniques that are highly uninterpretable or they're very difficult to interpret? Log models. So what do you mean by log models? So I'm seeing neural nets. So that's the big one that I kind of had in my mind. So neural nets are great. They've been shown to be more effective when it comes to predicting a given response variable value for large data sets. I want to add that key part here, for large data sets than the foundational algorithms. But something you always want to keep in mind is that a neural net is much more difficult to interpret than something like a basic like linear regression or logistic regression model. So we've already discussed two types of common supervised learning algorithms that we've heard of. So we've talked about linear regression, logistic regression, neural nets. And I'll say those neural nets that are specifically used for supervised learning analyses. Now, basically, a neural net can actually be used for a wide variety of different types of analyses. So actually, in this class, we'll introduce a type of neural net that is used for unsupervised learning purposes, but you can also use neural nets for supervised learning analyses as well. So I'm also seeing a random forest. Yeah, so random forests tend to be less interpretable than a regression model, but a decision tree, which is what a random forest is based on, also is quite interpretable as well. Yeah, and so some other common supervised learning techniques I'm seeing here in the chat are support vector machines, light GBM. Let's see here. I'm also seeing PCA. So let's see, K nearest neighbor. So PCA is actually going to be an algorithm that we will discuss in this class because it's technically an unsupervised learning analysis. And so we'll talk about in this today why PCA is actually an unsupervised learning analysis. But yeah, so these are some common supervised learning algorithms that you may or may not have heard of. And we know that they are supervised because we always assume that we have a response or a set of response variable values in our hands. And our goal is to build our model, or in other words, come up with the best mapping function G. Pen not working. Sorry, I'm just trying to get my pen to work here. The best mapping function G that predicts our set of response variable values. So for instance, in the case of ordinary least squares regression, we're not actually considering all possible mapping functions that exist, but we're simply considering just linear mapping functions. The way that we select, in this particular case, the best mapping function is the one that minimizes the sum square of the residuals. And the nice thing about a linear regression mapping function is that it's easy to interpret and we actually know what it is. Okay. So again, just to summarize, the main goal of a supervised learning algorithm is to predict the known given set of class labels or response variable values. Okay. All right, questions on that? Okay, so let's switch gears to what we're actually going to be doing in this class, which is unsupervised learning. So again, the overall goal of a unsupervised learning algorithm is to, again, or basically the key distinction here is that your response variable values are actually unknown. So basically, implicitly, these response variable values do exist, but we aren't actually given a set of response variable values in our hands or in the data set. But what we do have is a set of, why is my pen not working? Sorry guys, I might have to reboot OneNote. Sometimes it gets, I try to do too many things in this class, and then my OneNote gets a little bit overwhelmed. So just bear with me for 1 second. Come on. I'd like to say that this is not a common occurrence, but unfortunately it is. Okay. All right. Come on. Oh my goodness. Sorry. I'm trying to zoom in, but it will not let me do this. Oh my God. All right. Okay. So basically, with an unsupervised learning analysis, we can assume that there is some sort of response variable values, but we don't know what it is. Nonetheless, though, our goal, our theoretical goal is still the same. We still want to come up with the best mapping function that maps our set of explanatory variables onto this unknown implicit response variable values, such that our mapped explanatory variable values are as close as possible to our implicit response variable values. Now, given that we're not actually explicitly given a set of response variable values in our hands, this makes the task of fitting a unsupervised learning analysis much more difficult. So with a supervised learning analysis, we generally speaking know how well we did because we can measure how close our actual response variable values are to our predicted response variable values. So with an unsupervised learning analysis, we need to be much more sophisticated in evaluating how well our mapping function actually did when it came to giving us the values that we want. So you may have heard of some common types of unsupervised learning algorithms. I've kind of discussed them here already. So what are some unsupervised learning techniques that you might have heard of in the past? Okay, so I'm seeing k-means. Yeah, so k-means is a type or one algorithm that corresponds to a broader class of algorithms. So clustering. So k-means is a type of clustering algorithm. Hierarchical clustering. It's another type of clustering algorithm. Yeah, and then another broad class of unsupervised learning algorithms are what we call dimensionality reduction algorithms. So for instance, PCA, yeah, T-SNE plots, UMAP. Yeah, so basically we're going to be discussing all of these different classes, or these two classes of unsupervised learning algorithms. So clustering algorithms and dimensionality reduction algorithms. And we're going to be talking about all of the many different types of clustering algorithms and all of the many different types of dimensionality reduction algorithms, and specifically how and why we might decide to use each of these algorithms. So to summarize, the overall goal of a unsupervised learning algorithm is not necessarily to make predictions, but more so it's to discover hidden insights in the explanatory variable values or observations in the data set. Okay. Any questions on that? Okay, so let's talk a little bit more about what it is broadly that we're trying to do with the two main classes of unsupervised learning algorithms. So clustering algorithms and dimensionality reduction algorithms. So let's first talk about clustering algorithms. So generally speaking, the goal of any given clustering algorithm is to find a grouping of feature vectors or observations. Specifically, the groups in this grouping or clustering, we call them clusters. And a set of clusters, we call this a clustering, or a set of groups of observations. Now, generally speaking, an ideal clustering algorithm, or an ideal clustering, will be one in which the observations that were assigned to the same cluster are relatively similar to each other. And furthermore, observations that were assigned to different clusters are relatively dissimilar from each other. Okay, so I've basically spit out another vague, broad goal to you guys. So what are some vague things about this definition that I gave you here? Yeah, exactly. So you might furthermore ask the question, what does it mean for observations to be similar to each other? How do we measure? I'll say that. How do we measure the similarity between two observations in a given data set? And so the reason why we keep this element vague in this broader statement of our general goal of clustering is because this is one of the things that we would want to think about, or this is basically one of the decisions that dictates all of the many different types of clustering algorithms that exist in the literature. So for instance, k-means might have a different way of measuring closeness between two clusters. Or perhaps some of the other clustering algorithms that we're going to talk about use a different type of similarity metric. So the key thing here that you want to remember is that different clustering algorithms will use different definitions of observation similarity. Okay, so for instance, what might be one way that we could say that two objects or observations are similar to one another? Yeah, exactly. So kind of a basic thing that you could start with is, simply just using the Euclidean distance or the L2 norm. We might say that if the Euclidean distance is small, then two observations are similar. But this basically also, even if we're to like fix the distance metric that we're using, this also begs another relevant question that we would need to ask, though. So for instance, we might ask the question, how small does the Euclidean distance need to be in order for two observations to be considered similar, right? So for instance, if we take a look at this data set here, then we might say that, okay, these observations in this cloud, if they have a distance of about like 1, something like that, Euclidean distance of 1, they might all be considered similar to each other. But if we were perhaps looking at a different data set, is my pen not working? If we're looking at a different data set, or perhaps this was a cluster and this was a cluster, then perhaps we might want to change our notion of observation distance and say, okay, well, actually, if two observations are, within a distance of 3 from each other, then they're considered similar. So these are all things that we would want to think about when choosing the best clustering algorithm to use for a given data set. Sorry, OneNote is jumping around again. So let's replace. So for instance, We've talked about k-means clustering, and perhaps you've seen k-means clustering before, but k-means clustering is one type of clustering algorithm. And we want to think about, how does this map onto our general definition of a machine learning algorithm? So again, let's just say we were given simply just this two-dimensional data set here, and we wanted to cluster the data into sensible, let's just say 4 sensible clusters. So given that this is simply just a two-dimensional data set, we can see with our eyes that it makes the most sense to assign, for instance, a response variable value of 1 to these observations, a response variable value of 2 to these observations, 3 to these, and 4 to these. So in theory, the cluster label that we're assigning is our unknown implicit response variable value. And the k-means clustering algorithm that we implement is essentially providing that mapping function to us. It's basically saying these observations should belong to this cluster. These observations should belong to this cluster. But again, because there's no actual answer key for a unsupervised learning analysis, it's entirely possible that there could have been other cluster or clusterings that we could have come up with. So we really need to think carefully about how do we actually evaluate what is a good clustering of a given data set and what is not. So I'm already seeing some of those questions here in the chat already. So someone's asking, how would you choose the optimal number of clusters? And so there's going to be a wide variety of different techniques that you should consider when determining one of these important questions, which is how many clusters should you look for? So for instance, in the first unit, we're going to talk about something that we call a k-means elbow plot, and that'll give us a sense as to how many clusters actually inherently exist in the data set. So we can see with our eyes that there's actually 4 clusters in this data set. This makes sense to us. But the tricky thing, right, is like when you're dealing with a high dimensional data set, you don't actually know the implicit number of clusters to look for. So we're going to employ a variety of different techniques to hopefully help us answer that question. But the bullet point is there is, in this case, the best, and put big quotation marks around that, cluster labels in the case of clustering. That's what your unknown implicit response variable value is. And your goal in a clustering is to come up with the best mapping to give you those best cluster labels. And your output is the cluster labels. Okay, so this is broadly how a cluster analysis maps onto the general machine learning goal. So any questions on that? Okay. And so that's cluster analysis. And so the other main class of unsupervised learning analyses is what we call dimensionality reduction algorithms. And the general goal of these, or this broad class of algorithms, is to basically represent a high dimensional data set, usually with a lower dimensional data set, while preserving some aspect of the original data set's underlying structure. Okay, so basically this thing, or this aspect of the original data set that we're trying to preserve, is going to dictate all of the many different types of dimensionality reduction algorithms that exist in the literature. So different dimensionality reduction algorithms will try to preserve different aspects of the original data set. So, for instance, one of the most common types of dimensionality reduction algorithms that we'll talk about in this class in particular is PCA, principal component analysis. So we want to think about what aspect of the original data set are we trying to preserve with this algorithm. So let's just say, for instance, we two-dimensional data set. Why is my pen not working? We have this two-dimensional data set of like 5 students, and we've collected their heights. We decided to measure their heights in inches, and we've decided to measure their heights in centimeters. And one might argue that this is actually a little bit redundant, right? We don't need to have both of these column representations, but let's just say, for instance, that we do. So what we can do is calculate the variance of each of these 2 columns in the data set, and we can add up these 2 variances. to get a total attribute variance of basically 222. And so now again, there is inevitably some sort of implicit response variable value that we're trying to basically predict in this unsupervised learning analysis. So in theory, there exists some sort of variable y that will best pursue a particular goal that we're trying to achieve in this type of analysis. So in this case, our implicit response variable value y in this case is going to be a single variable representation of, in this case, this two-dimensional data set that best preserves what PCA is trying to preserve about the original data set. Let's think about what PCA, or let's explore what PCA actually tries to preserve. So basically, again, with PCA, as with any unsupervised learning analysis, we're trying to come up with some sort of optimal mapping function that makes or gets, so when we plug in our explanatory variables into that mapping function, it gets us as close as possible to this implicit response variable value. So we'll talk about how PCA actually works as we move on through the course. But basically, when we apply a principal component analysis to our set of explanatory variable values, we get this single variable representation right here. And so basically, if we take this new variable representation, we'll call it y hat, and we take the variance of that new variable, what we actually see is the total variance of the variables in the original data set is exactly equal to the total variance of the variables in this new representation. So basically, this is what PCA in particular is trying to preserve about the original data set. So in particular, we say that PCA is trying to preserve the total attribute variance of the variables in the original data set. Okay. So another dimensionality reduction algorithm that we're going to be talking about in this class, we call it TS&E or TS&E plots. That is going to be taking a high dimensional data set, representing it on a lower dimensional data set. But in that case, we're going to be trying to preserve something else instead. But the bullet point is PCA is trying to preserve total attribute variance of the variables in the original data set. Okay. All right, so that's a little bit about, kind of gives you a broad overview as to what we are going to be doing in this class, what is unsupervised learning. So yeah, any questions on that? Okay, so just a little bit more, and then we'll get to actually basically how the class is designed, how it's structured. But I also want to talk about the distinction between machine learning versus statistics, or generally speaking, inferential statistics. So the thing here is you can actually build a model, let's just say a linear regression model, for instance. You can actually build this model for two distinct purposes in mind. So you could actually build a linear regression model for machine learning purposes, or you perhaps could build a linear regression model for the purpose of inferential statistics instead. So the question is, how do you know when you're doing machine learning versus statistics? And so it's basically going to be based on the goal for why you're essentially building that model. So the general goal of any machine learning model is to build a model that yields good predictions, typically, for new data sets. Okay, so if you're building a linear regression model and you, for instance, would like for it to be used to effectively predict the response variable for new data sets, that might cause you perhaps to cut out, for instance, some explanatory variables that might be, overfitting. On the other hand, if you are building a linear regression model for the purpose of, inferential statistics, then the decisions that you make about, for instance, how to fit that model, like what variables to include, would be more for you to, pursue the goal of using insights from a random sample to make inferences about a larger population. So generally speaking, machine learning, your overall goal is to use your model, to basically to understand the data, to make good predictions. Inferential statistics, your general goal is to learn, specifically how to learn about larger populations. So, in the purpose of, building a linear regression model for inference purposes, you might, for instance, examine the p-values of each of these slopes to learn more about, whether you have enough evidence to suggest that slope in the population model is zero or not, or whether, for instance, there's an association between those variables in the population. So, for instance, you might make different decisions based on that goal. So you may choose to actually leave all of those variables in the model. Okay. All right. Questions on that? All right. All right. So let's get a little bit more into the general class information in the last 20 minutes. So, yeah. So we have basically two or three main platforms that we'll be using in the class. So you can check out the course schedule. And like I said, you basically, before the morning of any given class, you will be able to see the appropriate class materials. You can see the deadlines for each of the assignments, so on and so forth. You can look up information about me and the TA, Jordan, who's been assigned to this class. If you have any questions related to course content or any questions that are non-personal, I would suggest asking those questions on Piazza, basically, because you're more likely to get those questions answered more quickly as opposed to just sending me an email. We will be using Python in this course. If you've never used Python before, that's totally fine. We don't assume that you've essentially used Python. We do require that you have coded in some sort of programming language before. So in each of the applications, I will be going through all of the necessary functions in Python that you need in order to complete the homework assignments. But what I would say is, so basically I'll be posting the first homework assignment in Canvas this Friday. But if you've never used Python before, or if you've never, if you don't have Python set up on your computer, I would suggest going here and getting, following all these steps to get set up with Anaconda and Python in particular. And if you have any questions about that setup, you can reach out to me or Jordan in our office hours. Whoa, hold on a second. I'm in the wrong place. So the syllabus, wrong course website. Yeah, syllabus. So we can check out office hours. So I have my office hours every Friday. It will be starting this Friday. Jordan has his office hours on Wednesdays. You can take a look at that. Prereqs for the course. Definitely, you do need to have a linear algebra background. We will be making a lot of assumptions. We'll be relying heavily upon a deep linear algebra understanding. You do need a little bit of Stat 410, but generally speaking, we won't be relying too much on those techniques. Pretty much the only Stat 410 concept that we use in this class is the topic of maximum likelihood estimation. So if you're a little bit rusty on maximum likelihood estimation, I'd suggest reviewing that. But again, essentially what we're going to be doing in this class is we're going to be going through a series of the most popular foundational unsupervised learning algorithms. So a lot of these algorithms will not actually require knowledge of maximum likelihood estimation, but some will. So just keep that in mind. A couple of other things. So generally speaking, the course will be comprised of four main components. The largest amount of points, that this class involves is basically the homework assignments as well as the final project. There are two additional small point elements to this course as well, so we'll talk about that in a second. But yeah, basically, every Friday, I will be releasing a new homework assignment, and then basically you'll have a week to work on that homework assignment. So it'll basically be due every Friday. Yeah, so each of those homework assignments will be worth 30 points each. So you'll take a look here that, we do cap out at 300 points. So essentially what that means is you do get to drop the two lowest homework assignments that or homework assignment grades that you get. And basically the purpose of this policy is to essentially catch, any homework assignment that you need to miss for a variety of different reasons. And so if you find that you've had to miss more than two homework assignments due to, extenuating circumstances like sickness, so on and so forth, just get in touch with me and we can discuss options at that point. Late policy, basically, if it's more than 24 hours late, we don't essentially count it. If it's within 24 hours late, we basically just deduct 9 points. We do have regrade request policy. So if you feel that, you've been docked an undue amount of points, you can get in touch with Jordan within a week of getting that grade back. And basically just let him know, what you think you lost points on that you feel like you should get more points back for. And yeah, so basically the capstone, if you will, of this class is basically utilizing at least two of the algorithms that we have learned in this class, and basically using it on a data set of your choosing, and essentially performing a full beginning to end unsupervised learning analysis in Python. So basically your final project, you will work in groups of 4, basically conducting that analysis. Essentially the main parts of the project, you'll write up a report as well as present your findings. Basically, you can check the schedule as to when those presentation days actually are. 2 additional elements of the course. So we will have a smaller point final exam, I guess you could say. So I do want to make a point about this final exam. So let's take a look at the schedule here. So the final exam will basically be the very last day of class. And so like I mentioned, this is basically an online class, but the default setting for this final exam will be in person. So basically, if you know now that, due to extenuating circumstances that you won't be on campus at that time, basically you have until the 30th. That should be January 30th, to let me know if you foresee an issue with that. And then same thing for the final project presentations. The default, generally speaking, will be to present those in person. I will be there, watching your presentations. But again, if you know that there's going to be a problem, you have until the 30th to basically let me know. Okay. And then, yeah, so basically that final exam, the way to prepare for that final exam is it's not going to involve coding, but it will involve more of the interpretation aspects that you'll essentially be going through in the homework assignments. So the homework assignments should pretty thoroughly prepare you for, completing that final exam. So we'll talk more about that as the, semester progresses. Okay, I'm very much out of breath, which means I've been talking a lot. Any questions so far? No? Okay.
Okay. Oh, sorry, I have a question for the group assignments. So when will be the last day of forming a group?
Well, so can you say the last part again?
Yeah, sorry. What will be the last day of forming a group?
Oh, yeah, I would say, I don't know. I think it'd probably be a good idea to start thinking about your groups by like April. But yeah, I would say within the last 2 weeks of class, definitely have a sense as to who your group members would be. But yeah, you definitely have time to think about who you want in your group.
Okay, thank you. And so um for the data set that we're gonna choose, there's no restrictions on what kind of data set we have to use.
So there are going to be some restrictions. So we'll talk more about the exact specifications as we learn more of the algorithms in the class. But basically, the data set should be what we call clusterable, and that there should exist some sort of inherent separation between observations in the data set. Now, unfortunately, we don't actually have the tools yet to really evaluate whether a data set is clusterable or not. So once we learn how to do that, then I'll let you know how to go about evaluating whether a data set is good or not. But definitely think about some types of data sets that you might find interesting. Yeah, and someone's asking, will you post the assignment solution somewhere? So yeah, basically, I will post assignment solutions on Canvas. Okay. All right, questions, anything else?
I also have one more question.
Yeah, sure.
So will the lecture be recorded?
Yeah, so I record every lecture and I post them on Canvas within 24 hours.
Okay, thank you, Professor.
Sure. Okay. All right, a couple of other things, yada, yada, yada. I think that was basically, okay. Yeah, one other thing. One final aspect of the graded elements of the course is what I call checking Tuesday. And so this is really going to pertain to basically how we go about completing a complete unsupervised learning analysis, as well as how we complete our homework assignments. So I'll say this first about the homework assignments. So I would definitely encourage you guys, and I totally allow discussion of the homework assignments. So basically, every assignment that you submit should be done on an individual basis. It should be your own work, but you are allowed to talk about it with your classmates. You are allowed to collaborate, about it. But this should be your own work. So therefore, what I mean by that is that basically you should not, basically just copy paste your classmates' submission, essentially. So more specifically, you should not copy paste your classmates' submission and, simply just paste that into your homework assignment. And furthermore, you should not, electronically send your homework assignment to another classmate. So if we see any evidence of that, that would be a violation of academic integrity. So we would be, contacting FAIR, so on and so forth. But talking about your, individual assignments is totally fine. Now, there's this other element that I've had to, think about as a teacher, as we're, now obviously living in the world of ChatGPT and other AI tools. So the thing that you want to remember about, this class, as well as many, many other topics in data science, is that, and I'm sure you've seen this before, but like ChatGPT, it's kind of stupid. It does get a lot of things right, but it also gets a lot of things wrong. So the thing is, like, when using ChatGPT, you need to be really careful about evaluating the things that it's telling you, because quite often it's lacking in context and it gets a lot of things wrong. So therefore, I'm not necessarily saying that you shouldn't use ChatGPT. I would encourage you not to. I think it's a bad idea. I think you're much more likely to get things wrong. But what I will be checking for in this class is more a vital skill that I think is going to be important in your career, as well as the interviews that you're going to be going on as you enter the job market. And that skill is basically, do you understand the code that you're writing and the claims that you are making? Because basically just, relying on like copy pasting something from, Stack Exchange, or just copy pasting, something from ChatGPT, there can be a lot of consequences for not actually really digging into what was written and understanding that code or whatever it's, being said. So this introduces the idea of checking Tuesday. So basically, starting not next Tuesday, but the Tuesday after that, we will have a random check policy in place. So what'll happen is every Tuesday at 4:30, so basically 20 minutes before the end of class, I will send out an email to about 12 people in the class. So you should be checking your emails around that time, basically every Tuesday. And so basically, if you've been selected, what you will see in that email is basically a link to like a Google Doc, basically asking for you to explain your thought process for a question that looks almost exactly the same as a question that you just submitted in your last homework assignment. So the idea is basically, and I'm not even looking for the right answer. That's the thing. So if you don't get the right answer, that's totally fine. That's not what we're evaluating. What we're evaluating in the Checking Tuesday is basically whether or not you can explain your thought process for how you arrived at your particular answer. It doesn't necessarily have to be right. And that's essentially, when you're going to the data science interviews, I can't emphasize this enough, but like being able to speak aloud your thought process is such a useful tip or trick, I guess you could say, when conducting those interviews. But it's also going to be useful like in your career as well. Like, so eventually, inevitably, you'll have to explain your thought process to your boss, to your clients. So we're really trying to hone this skill here in the class, as well as my other classes as well. So yeah, so basically, if you have been selected, you'll have essentially 20 minutes, basically to the end of the class, to create a 10-minute video in Zoom where you're basically explaining your answer to the question that you've been given. And so you can use your homework assignment, you can use your class notes. Sorry, that's a typo. But basically, you're not allowed to use any other resources. So you can't talk to your classmates, you can't Google or anything like that. And yeah, so basically, as long as you're able to explain your thought process for how you arrived at that answer, and as long as as long as your video is like under 10 minutes long and you submit it before the deadline, then you should have nothing to worry about. So even if you get the wrong answer, you won't be penalized, but it's more, evaluating, can you explain your thought process? A couple of other things, you should make sure that your camera is on and that you share your screen while you're doing it. If you foresee an issue, like, if your camera's not working, let me know ahead of time, basically. Yeah, and then bullet point is like you'll be checked twice throughout the semester. And so basically each check is worth 7.5 points. Yeah, and the bullet point is that I want to emphasize this as well. So basically, if you do not get full credit on the check, I just want to emphasize this again. This is not me making an academic integrity violation. I don't necessarily think that you're cheating. It's more, this is a course outcome, that we're going to be evaluating on. Can you explain your thought process? And so simply, if you don't get full credit, then that's us saying that, you weren't really able to explain your thought process, basically. And so, yeah, so the bullet point is, again, I just, this is very chill. Like if you've put in a good faith effort to, understanding what you wrote down on your homework assignment, then this should be totally fine. Okay. All right. So that's basically, yeah, how the Checking Tuesday works. Here's the list of topics or algorithms that we're going to be going over in class. I think that's basically it in terms of course policies. Someone's asking, final exam, will it be multiple choice questions? I'm going to say it's going to be very focused on multiple choice. I would say at least 75%, if not more, it's going to be multiple choice. But basically, what we're going to be asking you about in the exam is basically like, we're going to take a data set and we're going to apply a arsenal of all the tools that we've learned in the class. And you basically need to come up with your best guess as to what that high dimensional data set actually looks like. And that's essentially what the goal of this class is. It's like learning as much as we can about what a high dimensional data set looks like that we can actually see with our eyes. Okay. All right. Any other course policy related questions? Okay. Couple of other things I really just wanted to quickly get to, just talking about just other things that we'll be essentially doing in the course. Just one final thing here is, again, yeah, we just, general goal is to, learn a series of tools that, allow for us to learn as much as we can. about high dimensional unlabeled data sets. But furthermore, some additional questions that we are going to be asking ourselves as we complete this unsupervised learning analysis is, for instance, how or when it is appropriate to, for instance, use a clustering algorithm or a dimensionality reduction algorithm in general. So for instance, you might have a data set that is basically just like a blob of points. There's no obvious separations that exist in the data set. So, as a data scientist, nobody's going to come out and tell you, like, you can't use k-means to cluster this data set. K-means will cluster this data set, and it might look something like this, right? Where you're simply just taking the blob and cutting it in half. And so the question is, these clusters that you've created here and that you're, showing to like a non-data scientist, are these clusters, are they actually meaningful? Like, are we perhaps misleading this non-data scientist into thinking that there exists some sort of meaningful separation of these points when there actually isn't? So one thing that we'll be evaluating is whether a data set is what we call clusterable, or in other words, should we even use a clustering algorithm to separate it into a series of clusters? So that's one thing that we'll learn about. Another thing that we're going to be thinking about is based on the data set that we're dealing with, what is going to be the most appropriate algorithm to use? So for instance, there's going to be some data sets that look like this. And so k-means would be, a fine algorithm to use to cluster this data set. On the other hand, there are going to be some data sets, for instance, in which your clusters look more like this. So we are seeing that perhaps there's a different notion of similarity. So we see these two, swirly clusters here, one here and one here. But if we use k-means to cluster this data set, k-means would not actually be able to find the two clusters that we can see with our eyes. So we'd want to think about what's going to be a more appropriate clustering algorithm to cluster, for instance, a data set such as this. In addition, we also want to think about, so once we've decided to use a particular, let's just say clustering algorithm, all of these algorithms require some sort of parameter tuning. So we want to think about what are the best parameters to use in this given clustering algorithm. So for instance, another question that we've already introduced here, right, is if we're dealing with a high dimensional data set that inherently has, let's just say, 3 clusters, like we can see here, how do we know that 3 clusters is the best number of clusters to look for? So we're going to be introducing techniques that can give us a good idea, for instance, as to what the best number of parameters to look for is. Really quickly, okay, well, I think I've run out of time. So we'll, if you want to learn a little bit more about the other questions that we'll be answering in this class, you can take a look at these questions here. But we'll cover this on Thursday. But basically, this just kind of details all of the things that we'll be, essentially evaluating you guys in this class. So otherwise, I'm super excited, for this class. Again, this is like literally one of my favorite classes to teach. So really excited that you guys are here. If you have any questions, feel free to let me know. Okay, so I'll stop recording.